dual path around the world and from academia back into the federal agency. And he's an expert in anything really forest-related diseases, pathogens. Sudden aspen decline, I believe, is going to be one of the main topics he speaks about today. So please ask questions and welcome Jim.
Wow.
Great introduction, Tom. Thank you. I'm impressed with
Myself.
So, were any of you at the seminar I did late September for the university? No. So that's good. So this won't be a rehash, because it is a lot of the same stuff I presented there, but Jessica Young gave me a short list of things she wanted me to add, so it's a little bit longer, but I call those things pedagogical asides because it's just things she wanted you to learn from what I'm talking about. So as Tom said, please ask questions. Don't wait till the end. Just interrupt, raise your hand. If I don't see your hand, just yell at me or something. And because it'll be much less boring for both of us if there's a little interaction during it, okay? So, as Tom said, I started with sudden aspen decline. That's how it got sort of into this climate change business. And from that, Suzanne's right here. She's one of the co-authors on a lot of this stuff. Got into looking at projections of climate change on aspen. And Jerry Rayfelt and Nick Crookston also work for the Forest Service up in Idaho for the Rocky Mountain Research Station, are kind of the big modelers in this area, developing bioclimate models. And so we went from looking at sudden aspen decline to modeling how it's going to develop in the future. And Andy Keck helped us with part of it, looking at the statistical analysis of some of the aspen plots we were working on. So another, way to look at this is the way we've developed it is trying to apply it to management. So we've taken the bioclimate models and applied them to management in terms of a strategy for managing forest adaptation to climate change. So the way we'll go about this is first a little background on sudden aspen decline, how we got into it, the history of it, and so on. And then getting into the bioclimate models and try to explain how they work and how we've used them. And then get into the more applied part of it, applying those bioclimate models to forest management, which I would say hasn't actually been done yet, but we're trying to push it now. And then really it's locally is where we've really been trying to do that, so the case study is part of that. So, sudden aspen decline, background. Over the last couple of years, we did a sort of a literature review and analysis of aspen declines that have been recorded throughout the range of aspen in North America over the last decade. And you see there are quite a few of them. This, I guess, purple or magenta, what is it, color, record that. Some of the things in the east, especially up in Ontario, northeastern Ontario there, are largely driven by insect defoliation, and climate plays a small part, if any, in that. In the Minnesota case, there's both insect defoliation and drought involved, so it's probably a half and half situation there. But in the western North America, from the Aspen parkland down into the southwestern states, that's pretty much all climate driven as far as we can tell, and in fact we're pretty sure of it. So let's look at the Southern Rockies here and get into the history of it. I guess I should just stand over here because So around 2002, anybody who was around in the West at that time probably remembers the big drought that we had. Really peaked in 2002, record-setting drought. And then in 2004, we got calls from a forester in Dolores talking about unusual levels of aspen mortality that were going on at that time. And the patterns of it were unusual. Not that mortality of aspen is anything new, but it was sort of on a different scale, which I'll explain in a moment. And then the year after, we got the aerial surveyors engaged in it to try to map it and measure it from the air. And then over the next few years, it spread throughout Colorado, throughout the aspen areas of Colorado and southern Wyoming. And it actually earlier had been popping up in Arizona, Utah, neighboring states, and also in the sort of the aspen parkland of Alberta and Saskatchewan, where the prairies kind of blend into forest and there's just patchy aspen there. It was very heavily affected. And then in 2008, that's when the aerial survey detection of this problem peaked. And in 2009, there really weren't new areas popping up after that.
Would you say earlier in those states, was that from the same 2002 drought, or were there earlier droughts in those?
It's a kind of a combination. In Alberta and Saskatchewan, it was clearly the 2002 drought, but for whatever reason, those aspen responded more quickly to it. In Arizona and Utah, drought conditions had been going on for a long time. Actually, I'll show you the trend of the drought, and it really started in the mid-'80s. And in Utah and Arizona, it was more severe than it was in Colorado, and so they began to have the thing pop up before that. So the way this thing looked in the field is as I said, unusual levels of mortality, but also branch dieback, crown thinning, leading to mortality. And it was on a really on a landscape scale for the most part, rather than a stand scale. When I said that mortality in aspen is nothing new, but it usually occurs on the scale of a stand. So, a couple acres, 5 acres, 10 acres, a stand that has a similar history and similar stand conditions, whereas this was occurring on the scale of a watershed, much larger area for miles. Not every aspen, not every stand in there, but when you look at a landscape from a vantage point, you can see that it's going on over a large area, and it's synchronized. So it was not a stand here and then a couple of years later a stand there, but synchronized over a large area. And one of the features of it was that it was kind of focused on lower elevations. So you see this aspen patch surrounded by sagebrush here is kind of a typical thing. And some of those small aspen patches were completely killed without any regeneration coming up. So even the roots were killed. So this is one of the pedagogical asides, I guess. Jessica wanted me to talk about how science is used in detection and characterization and communicating with managers when we find these things, either sudden aspen decline or spruce beetle or so on. And actually, it's not hugely scientific, I guess. Sometimes begins with just simple observations like sudden aspen decline did. We had a forester call us, and that's how it was detected. And that made us aware of it. We started looking around, seeing more of it. But when it gets big, something big that can be seen from the air, our aerial detection survey is a huge tool that we have to quantify and map these things, quantify the area affected, and to some extent the severity within the affected areas. So this is a big program that we have where guys fly around in airplanes and it's a cooperation in Colorado between the federal government, the Forest Service, and the state Forest Service. And they fly around and map these things with digital maps and so on, and develop a report every year. So that's been an important tool for us in sudden aspen decline. And you can import that stuff into GIS and do a lot with it, which we've taken advantage of. And then finally, I guess where it gets a little bit more scientific, we get into ground plots and surveys. And sampling design is very important for these things because you first have to know what you want to know and then design the plots to provide that information. And this really extends what we can learn from the aerial survey. So, kind of back to the storyline here. This event in Colorado began about 2 years after the peak of this turn-of-the-century drought. And I mentioned it began really in the early to mid-'80s. And the red graph on top there is a dryness index. So if that goes up, it's drier. And you see it climbing there. The other one is a moisture index, the blue one. And so that's somewhat the inverse, although it's based on a little bit different variables. And then the bottom one is modeled soil moisture, which you can get from a website where these guys have plugged all this information into a soil moisture model. So by any measure, this was a record-breaking drought within the instrumental period anyway. This is data for Southwestern Colorado. So we are pretty sure now that the drought was really the primary inciting factor for sudden aspen decline. And it's not something you can really prove experimentally because you can't do experiments of this sort at that scale. But here's some of the reasons, at least as of 2009, before the models came into the game, why we thought, I would say, that drought was an inciting factor. First, we had the drought, then we had the damage. So that's not rocket science, simple common sense. But we also observed leaf scorch on aspen in 2002, and the most common cause of leaf scorch is acute moisture stress. So it means that the trees just can't get enough moisture to keep the leaves wet, and the edges of the leaves dry out and turn black. Then the elevation relationship, we know that droughts are more severe at lower elevations because it's drier there, it's hotter there, and that's where most of the damage occurred too. And also, kind of the same thing on south to west aspects had greater damage than other aspects. So again, they're more exposed to the sun. Aspect is the direction that a slope points. So they're more exposed to the sun and the drying influences of the sun. So everything that we were finding was consistent. And then when we looked at the what we call the agents, the biological agents that were actually killing the trees, they were primarily secondary or stress-related agents, not the primary agents that can usually kill vigorous, healthy trees under normal circumstances. So stress-related agents, you usually want to think of what's the stress behind that. So let's take a bigger perspective on this drought, because I think it's really instructive when we think about the past and the future. These climate scientists, Schwalm et al., did a study of this drought throughout Western North America, and they found that you had to go back over 800 years to about 1150 before you could find a drought that severe in Western North America. So that's a pretty bad drought, you know, almost 1,000-year drought. Then they studied it in the perspective of the future by projecting the conditions over the coming century. So in this graph, the first half is the actual climate records for Western North America. The second half is mostly the projected climate records into the rest of the century. That little blip in the middle where the arrow is the turn of the century drought. So now it doesn't look so bad, right? Compared to the future.
Why is it basically a complete, like what variables are they taking into account? Because it seems like the complete opposite shift. Are they just expecting even more extreme drought to even occur in the future? Is that what
The y-axis is normalized precipitation, so it's just based on precipitation. Doesn't even take temperature into account. So this is using climate models that project a decrease in precipitation throughout Western North America on average.
Do you know which climate models were specifically
You know,
used?
I don't. It's most likely, most people use a number of models, but that's a good question. But this paper was in Nature Geosciences, pretty good journal, so, you know, a little bit trustworthy, although you're asking good questions, and that's the kind of thing the skeptical scientist should be looking at. I guess I'm a little bit less skeptical. But what these guys concluded is that by the 2030s, the conditions during the turn of the century drought will become the new norm in Western North America. That's their words. So that drought is going to be kind of the normal conditions. And then by the latter half of the 21st century, the precipitation regime associated with turn of the century drought will represent an outlier of extreme wetness. Extreme wetness. So the conditions that we had during that drought, the worst that we've seen in 800 years, will be considered extremely wet by toward the end of the century. So when you think about what that little blip did to our forests, we've got throughout the Southwest, the Four Corners area, Arizona, New Mexico, Utah, Southwest Colorado, we had a massive mortality event in pinyon pine caused by an insect, Ips confusus, but clearly triggered by drought stress. And that happened right as soon as the drought was peaking, 2002. Then we had sudden aspen decline, pretty clearly tied to that drought, and there's more evidence that I haven't shown you. We had mountain pine beetle in northern Colorado. Not completely drought caused, there's also stand conditions and so on involved in that. And I understand you guys took a trip up to see the spruce beetle around Slub Gully and Pass, which again, not all, you can't blame it all on the drought, but the drought certainly helped it build up.
How are you going to create a resiliency to these issues of precipitation? If already we had this one tiny thing and it caused a lot of issues already, is there a management plan to address these in the future?
Well, there isn't yet, but that's what we're proposing, and I'm going to get to answering that. And you know, it's a challenge, and the uncertainties in the future, and the fact that it's a moving target. You know, you kind of look at a point in the future, but that's just one point. It's going to be moving past that afterwards, and what time should you be planning for? That's another question. It's a difficult thing to grapple with, but I'll show you how we're grappling with it, and then you can judge.
Was this precipitation index, this is for if we were just to stay on course with status quo emissions?
No, no. It's using a carbon scenario, emission scenario that you have to plug into these. It's probably predicting an average of several scenarios, as that's what we use too. But these are good questions, and you also have to recognize that in these climate models, there's less certainty attached to precipitation than there is to temperature. And I'm not sure why they used precipitation here instead of a drought index, which would be combining precipitation and temperature. But you guys are looking at this pretty hard, and that's good. I should send you the reference. So my point is on that whole thing is when you look at that future and how much more severe it's going to be than the turn of the century drought, how do you imagine what that's going to do to the forest, the conditions that we're going to be dealing with? And I can't really imagine it very well, but that's where bioclimate models come in. They can allow us to deal with that question. So the way these work is that they characterize the climatic conditions that are suitable for a species. And what you do is you have many points where you know the species is currently either present or absent, and you have to have a historical climate, a long-term historical climate for those points, based on a grid of climate that's kind of interpolated from the historical climate. Then with that, you use this random forest algorithm in R to develop the model. Then you have the model. It's basically a mathematical equation, and you can then input any grid of climate to see what future would be, or the past. And what this is basically a map of climate where each pixel in the map is a set of climate variables. And then it outputs votes on the suitability of each pixel for the species in the future, ranging from 0 to 1 or 0 to 100%. And you can use those votes to make a map of suitability for the species based on the climate that you gave it. So here's a range-wide bioclimate model that Jerry Rayfelt developed for Aspen. And what you're seeing is the votes for the reference period, that long-term historic climate. And so the darker the green, the more suitable it is for Aspen, according to the model, and also the higher the probability of presence of Aspen. So, and this map follows very closely the actual distribution of Aspen at this scale. So no other information in there except for climate. Climate is really the 800-pound gorilla when it comes to predicting where a plant species is going to occur.
Is there a difference in the climate or like the habitat suitability for Aspen depending on how they grow? Because don't the ones on the East Coast, they don't grow clonally like the ones on the West Coast? Does that change how their habitat requirements, or?
You know, if you were to do, I don't know if clonality, per se is a big influence, but if you were to do the bioclimate model just for the East Coast or just for a small area in the West, for instance, it would come up with different climatic parameters that are predicting where the species should occur or where it should be suitable. It wouldn't be the same model. So what this is doing is just trying to integrate the best fit for the entire range of the species. And the East contributes to that, the West contributes to that, but you would almost certainly get different results if you just focused on one area. And that's what we did with the GMUG, as I'll show you in a little bit.
Well, in Aspen, we have a lot more competition in the east. That changes how they're able to spread. I think that's figured out.
So this is the model for the GMUG now, and I guess it's green is the votes from the model that are above 0.5. So roughly a threshold for suitability. If you know, really it's a continuum, but for interpreting things, it's helpful to put a threshold on it. So this model is optimized for the GMUG because it's based on GMUG data that was built using GMUG presence and absence and associated climate. And it also takes into account aspect and slope. So it's a little bit more refined in that regard. And it's mapped on a finer scale, which is more useful for management. So again, the green is representing areas that are predicted to be suitable by the model from the reference climate. So this is not a prediction of the future, it's a prediction of the current distribution. And we know the distribution within the GMUG, those black outlines there are the GMUG. We don't have as good information outside the GMUG, so we've only tried to map the actual Aspen distribution inside. So if you look inside, the blue is the Aspen cover based on, you know, pretty good information from the Forest Service records. And where they overlap is, what is it, teal? Yeah. So most of what you see inside the National Forest is teal. You see a little bit of blue here and there where the aspen actually exists, but the model didn't think it was suitable. We call that an error of omission because the model omitted it. And you see a little bit of green inside the National Forest where the model said it should be suitable, but it isn't there. That's an error of commission. The model committed to saying it was going to be there, but it wasn't. And there's some explanations for those kinds of errors that where you wouldn't fault the model. For instance, especially errors of commission can be places where it is suitable for aspen, but because of the disturbance history or whatever, there just hasn't been aspen there. Or maybe it's bare rock, or maybe it's water. You know, the model doesn't know that. All it knows is the climate. So those things we're not too worried about. Errors of omission are a little bit more troublesome in terms of the model. But by and large, it does a fantastic job of duplicating the actual distribution of aspen within the GMUG based on the historic climate.
Jim, can you give some spatial reference for the whole GMUG area?
You know, I have a map later that does much better. I should have shown that first. But Gunnison is about right here. Crested Butte up there somewhere. This is the West Elks. Okay. This is Cochetopa Park. Monarch Pass over here. Uncompahgre Plateau, Grand Mesa. Yeah, should have shown that other map first. So here's another way we used the model. We put, the red here is where we had the sudden aspen decline mapped from 2000 to 2010. Really, it was pretty much 2005 to 2009. And the blue and green scale is the model where we fed it the climate during the decade that led up to that, so 1997 to 2006. And so the blue is where the suitability for aspen decreased during that period relative to the reference period. and the green is where it increased. So what we did is we took the output of the model from the reference period and the output of the model from the that decade, and then we subtracted them to develop this. So we got increase and decrease in suitability. And by and large, the decline occurred where there was a decrease in suitability during that decade. So the other thing Jessica wanted me to talk about is uncertainty, and it's a really good topic that we need to pay attention to. So let's talk about uncertainty. Sources of uncertainty in general is errors in the presence-absence data that were used to build the model. So, on the GMUG, that data was derived from aerial photographs that are photo-interpreted. So people study these photographs to see where the aspen is. They try to recognize the aspen. Maybe sometimes they're seeing cottonwood and they think it's aspen. Or maybe there's aspen in the understory and they can't see it because there's conifers on top of it. So there might be errors in that data, and those errors go into the model because we're saying absence or presence based on that. Then you have the errors of omission and commission, which I talked about, that are, mean that the model is not perfect in predicting presence and absence, although it's probably better in predicting suitability and unsuitability. And then there's inaccuracies in the climate data because, we don't really have exact climate data for every little point on the Earth. This is all interpolated and downscaled from weather records at stations. I would say that Jerry Rayfelt has probably the best procedure for doing this and better climate data even than the PRISM data, which a lot of people use. Then when you try to project into the future using future climate, you have additional sources of uncertainty. One is the carbon scenarios. This is a huge one, which somebody brought up. We don't know how much carbon humans are going to be emitting and other greenhouse gases through the rest of the century. We just have to guess. And a lot of smart people have put together these various scenarios, which you probably read about. I know you read about a climate modeling paper from 2006. You were assigned that, and I looked at that, and they were using the earlier climate or carbon scenarios that were developed for the fourth edition of IPCC's report. Now we're using more recent ones. The IPCC is now using these RCPs, representative carbon pathways, and there's 4 of them, 2.6, 4.5, 6, and 8.5. The 8.5 is a very dire scenario. 2.6 is very pie in the sky. It's all going to be rosy in the future. We've already stopped, we've already started reducing our carbon, and that's going to continue into the future. And the radiative forcing is going to peak later in the century and then start decreasing. And so it's going to keep temperature increase to a fairly modest amount. A lot of people don't think that 2.6 is very realistic, so we didn't use it. But what we did use is the other 3. And then the general circulation models, there's a ton of these models that IPCC uses. I think there's like 25 or 30 of them. And we used output of the 3 common ones. And these models vary. So one might give you very different results than another, and you don't know which one is right. The problem with this stuff is you can't really put probabilities on it. You can't say there's a 90% probability that the climate is going to be such and such in 2060. So we used 3 of the common models, and then what we did is, so we took the 3 scenarios and the 3 general circulation models, worked them all against each other, and we got 9 projected climates, and ran the bioclimate model with all 9 of those climates, and then averaged the results. So the votes that came out from those 9 runs for each pixel is then averaged into one result. Now you could look at the variability among all 9 of those things separately, but it's just very difficult to do, and I'm not sure it really adds a lot to the discussion, and particularly when you're trying to develop management plans, a little bit too much information.
Yeah, we tried that.
Yeah. So the way I look at this uncertainty thing and the way Jerry Rayfelt looks at it, the bioclimate model is actually quite strong, because when you feed it the recent climate, it tells you where Aspen should be, and it's pretty good. It's pretty good. The GCMs, people can argue with them, but they're pretty good too. The best minds in the world have developed these things, and they've done all kinds of testing on them that you wouldn't believe. I mean, there's been a lot of work invested in testing these things, usually by predicting the past. So even, thousands of years ago, they put these models based on what they know about the conditions at that time, and they do a good job of predicting climatic changes. Most of the criticism that comes to these models, except if it's coming from climate deniers, is that they are too conservative in predicting climate change. But, as I said before, we can't predict the future climate and assign probabilities to it. We can't, that just can't be done. So some people would say that you can't predict the future, so why do you even try? This is all meaningless. You can't tell me that is any more likely than green Martians coming to Earth. But really, my answer to that is we have to. We have to predict the future. Everything we do as human beings builds into it an implied prediction of the future. When somebody builds a house, do they put in a heating plant? Do they put in air conditioning? How much insulation do they put in? Everything you do, it isn't just about climate either. And if you don't predict the future, then by default, you're expecting the future to be just like the past. And we're pretty sure that's no good anymore. So we have to come up with the best prediction we can, and that's what we're trying to do. If somebody comes up with better models and so on in the future, then we can use them. But all this uncertainty, to me, boils down to uncertainty in time. So, we're projecting 2060 that these certain climate state is going to occur. And, maybe it'll be after that, maybe it'll be before that, but it's probably going to occur. It's pretty likely. And the exact time that it happens is less important in terms of trying to prepare. So let's get into forest management now. Probably going way too long here. Forest managers know about climate change. We hear about it a lot, and they know it needs to be considered. Forest Service policies dictate that climate change be considered in forest planning and management. And as I said already, if you don't plan for the future, you're planning for the past. So if we don't plan for the future, we can expect a lot of ecological havoc out there. We know that the rate of climate change that we're expecting is far greater than has happened in the past, and is greater than the capacity of ecosystems to adjust. So it could take thousands of years for communities to reassemble in any kind of way that we're used to seeing now. So we'll have degradation of ecosystem services, loss of biodiversity, and the hydrology implications. It won't be pretty. So the problem with managing for this is that it's a huge issue. We have the uncertainty, which is kind of paralyzing to a lot of people. And it's unprecedented. People don't have the training to deal with it. And there's a lot to do without adding climate change to the mix. And I think one of the problems too for Forest Service employees that are trying to deal with it is there's really too much information. We really get hit hard with emails all the time and all this stuff, climate change studies, data, links, and to try to help managers, the researchers put out these conceptual approaches and strategic frameworks and tools for analyzing goals. I mean, researchers, the research community, everybody tries to be state of the art and sort of on the cutting edge so that they can build a name for themselves, and clearly climate change is where it's at. So there's a lot of information coming out, and I'm not saying it isn't good, but it's just hard to sort out, what do I do with it? How do I deal with it? So what we really need more of is concrete examples of how to actually develop a management plan. So that's what we're trying to do. On the GMUG, we had sudden aspen decline, which affected 33% of the cover type. And we know that damage stands have continued to deteriorate. And this is the results of our plot studies from last year in the sudden aspen decline stands. So we have the sick plots on the right. Those have continued to deteriorate. So we have the 2013 data in the white. You see we have less live basal area, less recent dead basal area, and more snags basal area. The healthy plots haven't really changed much. This is recent crown loss now, and you see healthy plots again haven't changed much, but in 2013 we found less recent crown loss in sick plots than during the SAD epidemic, but still much higher than in healthy plots. So it shows things aren't deteriorating as quickly as they were before, but they're still deteriorating compared to healthy plots.
Are those lines standard deviation coming up for those plots?
The lines are medians, and the diamond is a mean.
Do you mean the whiskers?
Yeah.
Oh, the whiskers?
Yeah.
Oh, I'm sorry. The horizontal lines are the means, are medians. The whiskers is, I think it goes beyond the box to include, I think it's the same number of observations as are inside the box. I can't remember.
The other quartiles, so there's 4 sections, right? So there's 2 in the box and 2 outside the box. So half of the data fits inside the box, and then the other half is the whisker.
Well, not exactly though, because there are also outliers here,
Right.
which are not included. It's where the non-outliers outside the box find. As Suzanne said, the box is the 50% of the observations are inside the box, and the rest of them are on the lines except for the outliers. Basically, that's the only way I can explain it without looking it up. And then also in those plots, regeneration is decreasing, so we see sucker density here. In suckers are the regenerating sprouts from the roots. In sick stands, there's now more that are close to 0, and we've lost some of the middle levels of regeneration. So bottom line is those SAD stands are continuing to deteriorate. And then we have the spruce beetle, which you all saw, which is another major problem for the forest. So as you probably heard on that field trip, the forest is developing a forest-wide environmental impact statement to work out a project that's planned for 10 years. And it's the spruce beetle epidemic and aspen decline management response, which we lovingly call SPEEDMR. And the plan is to treat 70,000, around 100,000 acres over 10 years, either mechanically or with fire. And that would be spruce and aspen. And the objectives are hazard tree removal, salvage. So hazard trees are trees that might fall on roads and campgrounds and so on. Salvage, getting the value of the wood from some of the dead trees to send to sawmills and firewood and so on. And then increasing the resilience of spruce for the future, and aspen as well. And then in aspen, we also want to regenerate deteriorating stands. So our strategy for a project like this is that we start out, we look at the projections for aspen and spruce into the future, and to project future suitability. And we're using Rayfeld's improved downscaling process and so on. And then we take the difference between the reference period and the future to classify the aspen and spruce into change zones or habitat something, whatever. We haven't agreed on what to call these. But so again, the models put out 0 to 1, right? Suitability. And what we've done is categorize these changes into 4 classes. And so, for example, the lost category starts out in the reference period, it's greater than 0.5. And then in the decades surrounding 2060, it's less than 0.3. So that's a big drop in suitability. And what we're doing, rather than just saying less than 0.5, is we're trying to be conservative in saying the habitat is lost or that the suitability is lost. And so this adds a little bit more certainty that it really is lost. And then what we did is we put that other bit, the 0.3 to 0.5 in 2060, into threatened. So it's suitable now, it's above 0.5. In the future, it's going to be 0.3 to 0.5, and so that's threatened. And then the persistent is where it stays above 0.5, and then the emergent is where it is below 0.5 now, so not suitable, and then it becomes suitable in the future. So new habitat for aspen and spruce.
Have you attributed probabilities to each of these?
No, we can't. We don't have any way to do that. We can be relatively certain, like with the lost, because we're being conservative in that, we're relatively certain that it's going to be lost. But, probabilities are nice if you can do them, but we can't. And there are people who would say, then don't do anything, And I've already made that argument with you. So then we take those zones and we develop management tactics that are suitable for each zone and apply them where they'll be most effective. So this is the map I should have showed you earlier. We're right here, and we have this is Suzanne's pride and joy here. Shows you elevation and the forest boundaries and so on. So the Grand Mesa is worth noting, and the Uncompahgre Plateau here, and the Continental Divide on the east and south. Let's try that again. Well, we lost the most important map of the whole set here. Yeah, that is really something. Well, we're going to have to. Pardon?
Is that the management map?
Yeah. So imagine, if you will, a map of the change zones. So we have lost, threatened, persistent.
Are we gonna pass it around?
Um,
Is that the one?
that is an older version of it. That's based on the range-wide model. The new one is based on the GMUG model, and it's higher resolution. But it could give people an idea if you want to pass it around, sure. So we have different colors for lost, threatened, persistent, and emergent. And as you might expect, there tends to be more lost at lower elevations. There definitely is an elevational influence. The emergent habitat tends to be at high elevations. Basically, for Aspen, the Uncompahgre Plateau is almost all lost. So it goes to a suitability of less than 0.3 in the decade around 2060. There's a little bit of threatened in some protected north slopes and ravines and so on. But pretty much all lost. And the Grand Mesa, a lot of it's lost on the south slope of the Grand Mesa. On the north slope, it's mostly a mixture of lost and threatened. There currently isn't good habitat for aspen on the top of the Grand Mesa, but there is some emergent, a little bit scattered around. In the rest of the areas, it's pretty much an elevational thing. So there is pretty much what you'd expect. But there's a lot of lost. I should have had a slide with the numbers for how much was in it, but I think it was something around 40-50% of the currently suitable habitat is in the lost category.
Has there been studies looking at like maybe loss of select species due to aspen loss?
Due to losing aspen?
Yeah.
There was, I don't think there have been any real good projections of it, but Bill Anderegg did a study down on the San Juan National Forest of sad stands, and where he did quantify loss of changes in forb and herb cover and species diversity in sad-affected stands where the canopy was opened up versus non-affected stands. There was an increase in shrubs he found and a decrease in herbs and forbs, and there was a decrease in species diversity in the sad-affected stands. So he, argued that that's what, the effect of climate change would be. So, based on the change zones, what do we want to do? Well, there's two things that we can do with aspen. One is we can try to increase the resilience of aspen, and as I'll show you, we know that young aspen is more resilient to drought than old aspen. So regenerating mature aspen is a good way to increase resilience. And recovery is another one, so sad-affected stands, before we lose about 50% of the stand, we can bring it back. Otherwise, it's likely to continue to deteriorate as we've shown. So resilience of youth, this is a patch of young aspen that was cut in 1984, and then the roots all sprouted, new suckers. So when we took this picture, I guess it was I don't know, about 35 years old, something like that. And you can see that the aspen around it, the whole landscape is deteriorating, but that patch of aspen is the healthiest patch in the whole area. So this observation was made all over the place, and basically under about 40 years old, was unaffected by sudden aspen decline. So age diversity in this case did increase resilience at a landscape scale. And then cutting, bringing aspen back. There have been a couple of studies of this where there were different levels of SAD, so high, medium, and low. And this is the control plots that were not cut. And then the plots that were cut, this is the regeneration density in those plots. So you see that where you had low amount of SAD, the response was very good. Where you had a high amount of SAD, the response was less. And so there's another study that shows more starkly that once you get above about 50%, that you're less likely to get much of anything. I showed this one because it's done on the GMUG.
Where was that study done?
It was done north of Paonia on the Terra Creek watershed.
And also, were they using exposures or were they just cutting and monitoring?
No exposures. The other study in Utah that I mentioned, I have a slide for that too, but I didn't bring it. He did use exposures. You know.
Some of this may be attributed to like a lack of disturbance, like human specifically, like fire, or maybe be different.
Yeah, you know, there's so many things at play here. In the absence of sudden aspen decline, you could expect to lose cirral aspen stands. So aspen would, in many cases, not all, gradually be replaced by conifers. And you could do something like this, cut it to reset the succession, you know, at the beginning. Aspen is at the beginning. So it's definitely a potential factor, but this, I think, is you know, this is sudden aspen decline. It's not due to lack of disturbance, you know.
How many of these stems actually reach maturity?
Pardon?
This graph just talks about regenerating stems. Are these stems actually reaching maturity, or are they being?
Most of them will not. The density is, you know, off the charts here. You know, you've got 100,000 suckers per hectare. By the time the stand is mature, you're only going to have, you know, 150. So, yeah, most of them won't survive. But the more you have, the more likely you'll have a full stand when all is said and done, because you will have herbivory, you will have diseases and insects and so on. And there's a lot of natural self-thinning in aspen. But it's been shown that if you can't expect to start out with 150 suckers and end up with a stand of 150 mature trees. You need a lot to ensure success at the end. And this doesn't guarantee that they'll all survive, but it's more likely. So where do we apply these treatments? In the loss zone, I think it's pretty much hands-off is the best strategy, because aspen doesn't have a good future there. We don't need to invest, we shouldn't invest resources into treating it there, unless there's some short-term benefits like improving wildlife habitat or something. In the threatened zone, this is a really good place to do both kinds of treatments, the resilience and the recovery treatments, to increase the likelihood of aspen survival in future severe droughts. In the persistent zone, we're looking at normal management. You know, we can do recovery treatments there if we want, but not really needed. And then we have some treatments that we can do there and in the emergent zone to help facilitate the migration of aspen in the future. And got just a couple slides about that. Well, one slide really. So the idea is we have a persistent zone where we have aspen and a nearby zone that's emergent, where we expect it to become suitable for aspen in the future. We need to make sure, one idea is to make sure that we have a good seed source for the aspen in these emergent zones so that the seeds can disperse to the nearby emergent zones. Aspen seeds are very light and easily wind dispersed. So in cases where we already have that, we have female aspen. Aspen is, has male and female clones. If we have female clone nearby that's doing well, that's great. But let's say we have a stand where there's aspen is being crowded out by conifers in the successional process that we talked about. We could go through there and reset succession, cut it out, and have new suckers coming up to produce a pure aspen stand where we'd have a better seed source in the future. Obviously, we'd want to do this where we have female aspen, and there's also some ploidy issues involved, but don't want to get too in the weeds here. Then, in the future, when that area becomes emergent, there's probably going to be natural wildfires in there. If there isn't, we could have prescribed fires or cutting to create a seed bed for aspen, and then if all goes well, the aspen seeds will colonize that area and move into the emergent zone. So planting aspen really isn't a very good option, and it's a lot more expensive than doing something like this.
There have been studies to look into whether the aspen will take advantage of areas that have been hit hard by the beetles. Will they move into
Yeah, people are looking at that, and it is doing well in where aspen already was there. It's doing well in some of the beetle-affected stands. It always does well in fires too. So disturbance is great for aspen, any kind of disturbance. So getting close to wrapping it up here. Here's the spruce version of the missing aspen map. So we have lost. This is almost all lost on the Uncompahgre Plateau. Uncompahgre Plateau now has a lot of aspen and spruce on it as two of the main forest types. So it's going to be hit pretty hard, most likely. On the plateau, we have lost around the fringes of the spruce and threatened on most of the top. A lot of threatened. There's really not much persistent except in the Lagaritas here and some of the San Juans. And we have a mixture of lost and threatened in the West Elks. The emergent is really at high elevations, and frankly, a lot of that is probably rock and scree and so on. But what we can do with spruce, a couple things. One is type conversion is probably a good idea in a lot of spruce stands. We can favor or plant species that are more drought tolerant. They're drier forest types. Douglas fir, blue spruce, lodgepole pine, and even aspen. We can increase resilience by reducing the basal area, just the amount of tree out there, so that there's less competition for the limited amount of water. And there's also different genotypes in spruce that are localized to their own area. So transferring seed from areas where it's drier, lower elevations, up to upper areas is probably a good idea. And then finally, salvage is a thing to consider too. So where do we do it? In the lost zone for spruce, again, we probably want to stay away from it unless we're confident that we can either regenerate with spruce naturally or convert it to more drought-tolerant forest types. In the threatened zone, this is, we could consider either resilience treatments or type conversion there. And in the persistent zone, restoration efforts, planting spruce, using seed transfer guidelines that are adapted to climate change, and salvage is a good idea there. And then in the emergent, as conditions change, planting could be done. So wrapping it up here, I think some of what we've seen, especially with SAD, can be considered at least similar to what we're going to see more of in the future. You know, attributing it to climate change is problematic, but droughts like the one we saw are definitely more likely because of climate change. And if we don't actively deal with trying to help the forest adapt with that, I think it's likely that ecosystem services will degrade and we'll lose a lot of things that we depend on from the forest. So classifying change zones is one way to do that, these management zones or whatever we're going to call them, because they help us anticipate change and focus management where it's going to be most effective. You know, if we go out and try to spend a lot of effort restoring spruce into those lost zones, that's a big waste of effort that could be better used to help spruce adapt in areas where it has a chance. And that's why the future has already arrived. So I don't know if there's any more questions that you didn't pop up with at the beginning. That's sorry, that's the longest talk I've ever given. It's hideous.
You guys are doing a lot of public engagement with the Speed Mark plan, so you have a pretty big audience. How are they reacting to these models? Like on the Pine Plateau, you know, somebody that lives in that area and depends on that forest sees that you're pretty much writing it off based on models that, you know, they may not understand, or they may have different theories of why these mismanagement sort of. So how, I guess, have you gotten a lot of criticism?
No, that's a great question. There hasn't been, I mean, I think people wanted the Forest Service to address climate change. There was movements in that direction early on, or suggestions. When we presented this, there wasn't really a whole lot of comment, yay or nay, from the general public. I think, like you say, it's a little bit shocking to see some of the projections, especially a lot of those people that are heavily involved in this are from the Uncompahgre Plateau. I can't remember the name of those organizations. ULP or UPLP or something. PLP. A lot of them are kind of around the plateau, and yeah, it's a little shocking, but they haven't really said much. We have had criticism from scientists at CSU that, as I hinted, they're not involved in this project, but as I hinted, there have been people who say, you can't predict the future, you know, this is no more likely than anything else, etc. We've had long email debates with these guys, Jerry Ray felt involved too. And I don't fully understand the viewpoint or what it's driven by for those guys. I can understand being skeptical and conservative, but you know, given all the uncertainty, I think we have to go with what we think is most likely, even if we can't put a probability on it. So I guess there is some controversy about it, but you know, bioclimate models in general. But it seems like the best way to go, the best way to plan for the future.
Well, I think part of it is a lot of people want to let nature take its course. Like if you're in college or sometimes you think, well, nature's been working with climate forever. But like you pointed out, we're thinking about ecosystem services too, and want our forest to look weird.
Yeah, that's a good point. A lot of people say, yeah, climate's going to change. It's changed in the past. Just let nature take its course. That's, that's a possible viewpoint. I mean, it's changing much faster now than it did in the past, and we don't really know how things looked. I can pretty much guarantee you people aren't going to like what happens.
Right.
They don't like mountain pine beetle. They don't like spruce beetle. They don't like sudden aspen decline, and it's not going to get any better.
Right. And I think you'll get a good case study, because you guys can't do this in wilderness areas, right? You can't manage in those areas, is that true?
That's true.
Actively
Yeah.
manage, right, so you kind of be able to see how they respond versus how you guys manage.
Yeah. Oh, yeah. I mean, there's actually a small portion of the forest that can be managed with mechanical treatments. The rest can be managed with prescribed fire outside of the wilderness areas, but there's access issues and all kinds of limitations on prescribed fire. So no matter what we do, it's going to be a small part of the forest. I can't remember what, I think the amount that they're talking about, the 100,000 acres over the course of the 10-year EIS, which is split between mechanical and fire, we don't know how much of each, is, what's 3.65 million divided by,
Yeah, I heard it was 5% or something. I think it was
Yeah, sounds about right. Yeah. Well, you guys ask good questions, I tell you.
Is there any uncertainty of or what is the uncertainty of the adaptive capacity of the aspen and other species to actually respond to these drought rings on this short time scale? Is there?
Yeah, that's another good point. People point out that aspen occurs, it has the widest range of any species in North America. It occurs in all kinds of conditions and sites, from moist to dry, and clearly has a very wide ecological amplitude. And yet, it is very sensitive to drought. Wherever it is, I guess wherever it can survive, it kind of is, whether it's genetically or physiologically, it's adapted to those conditions, but when they change greatly, it doesn't seem to fare well. There is a lot of potential for genetic adaptation, but that is going to be so much slower than the rate of climate change. I don't think we can rely on that. We can help it by moving seed zones around to where they'll be better adapted. Because the climate that seed zone, is adapted for is moving. So what the best thing to do is move the genotype with the climate.
With your adaptive management plan, you guys talk about incorporating new scientific understanding a lot too that comes along to be able to adapt. I guess what kind of gaps do you see, or that you fill in the future? Either to better manage the forests or automate your models, or?
Well, I can't speak for the whole SPEEDMER EIS effort, but with what we're doing, one of the most likely scenarios for change in our understanding is possibly better bioclimate or other types of vegetation models that can take climate into account. That more people will get behind. Actually, most people are behind these, but there's a few loud naysayers. But as better models come along and better climate methods and so on, better climate models, You know, these things can be constantly revised and updated. So, I mean, we've already done it. You had the map that you handed around there is the first iteration from last year, and we've already approved on that with a GMUG specific optimized model. So, yeah.
Are there any other questions? Well, great questions, everyone. Thank you very much.